What if the darkest things in the universe are also the key to its biggest secrets? And what if just beyond that point of no return, black holes aren't just empty voids, but the source of the mysterious dark matter and dark energy that dominate our cosmos? For decades, we've pictured them as cosmic prisons, engines of pure destruction. But that picture is starting to change. Some scientists are now asking a revolutionary question. What if black holes aren't the end of the story? What if they are active, powerful, and deeply connected to the 95% of the universe we can't see? Let's take a journey to the event horizon and beyond, to explore the new dark side of black holes. We all find paradoxes that challenge reality itself and ask whether the answers to our greatest cosmic mysteries are hiding inside. The lure of the abyss. To understand the dark side of a black hole, you first have to get near one. Picture it. You're in a ship, floating through the dead quiet of space. Ahead of you is a spot of perfect blackness, a hole punched in the very fabric of reality. It doesn't shine, it doesn't glow, it's just gone. As you get closer, something strange starts to happen. The starlight from behind the black hole begins to bend and warp, creating a ghostly halo of light around the darkness. This is the first warning sign. You're entering a place of truly extreme gravity, where space itself is being pulled into the abyss. Your ship's sensors would scream with warnings about tidal forces, the same forces that create the terrifying idea of spaghettification. The pull on the front of your ship would be so much stronger than the pull on the back that it would stretch you, atom by atom, into a long, thin noodle of what you used to be. But the story is different for a supermassive black hole, like the one at the heart of our own galaxy. These giants are so huge that the tidal forces at their edge are surprisingly quite gentle. In theory, you could drift across this boundary without being torn to pieces. This boundary is the event horizon. It isn't a wall you could touch or a line you could see. There are no warning signs, no cosmic buoys. According to Einstein's relativity, the moment you cross, it would feel completely normal. You might not even notice. But that quiet moment hides a simple, terrifying fact. You have passed the point of no return. You've crossed a one-way door in space-time. Behind you, the universe carries on, but you can never go back. Any light you shine, any message you send, is now trapped, destined to fall forever toward the heart of darkness. It's a quiet, final goodbye to everything you've ever known. You are now inside the black hole, where the rules of the game have completely changed. A tale of two theories, so what's actually in there in the heart of a black hole? This question forces a head-on collision between the two pillars of modern physics. Einstein's general relativity, our theory of gravity, and the very large in quantum mechanics, our theory of the very small. According to Einstein, everything that falls in gets crushed into a single point of infinite density at the center. The singularity, our laws of physics simply give up. They stop making sense. For decades, physicists have been searching for a theory of quantum gravity that could fix this breakdown and tell us what really happens when you squeeze matter that hard. But the singularity isn't the only problem. Event horizon itself has become a battleground. While Einstein's theory says crossing it should be smooth and uneventful, some quantum theories predict something way more violent. This is the firewall paradox. The idea is that if all the information that falls into a black hole isn't lost forever, it must get out somehow. To make that happen, some theories suggest that a blazing hot wall of high-energy particles exists right at the event horizon. In that version of reality, anything that tries to cross a star, a planet, you would be instantly vaporized in a blast of quantum fire. So we have a stark choice. Is Einstein's smooth horizon wrong, or is a fundamental rule of quantum mechanics being broken? Does a traveler fall gently toward the center, or do they hit a wall of fire at the edge? This isn't just a small detail. It's a fork in the road for physics. The answer, whichever it is, will force us to rewrite our understanding of gravity and space-time itself. It means the dark side of a black hole might start right at its edge, with a violent barrier protecting whatever secrets lie within. The information paradoxed back in the 1970s, Stephen Hawking discovered something that turned physics on its head. He realized that when you mix quantum mechanics with black holes, they aren't perfectly black after all. They give off a faint thermal glow, which we now call Hawking radiation. Over incredible amounts of time, far longer than the universe has been around. This slow leak of energy means that a black hole should eventually evaporate and disappear completely. But this created a huge problem. A core rule of quantum physics is that information can never be destroyed. It can be scrambled, hidden, or rearranged, but the basic information describing something can't just vanish. If a black hole disappears, what happens to the information about all the things that fell into it? Hawking's initial work suggested the radiation was random, meaning the information was gone forever. This is the black hole information paradox, a cosmic mystery where the laws of physics themselves seem to be on trial. For 50 years, physicists have been wrestling with this. While the paradox is not considered fully solved, a major theoretical breakthrough has given us a powerful new clue. It seems the information does get out, cleverly encoded in the Hawking radiation. Recent calculations, based on a concept called the page curve, show that the randomness of the radiation changes over the black hole's life. It behaves exactly as you would expect if the information was being slowly, painstakingly released. Think of it like burning a book. To you, the information is gone, lost in a cloud of smoke and a pile of ash. But in principle, a super advanced physicist could collect every single particle of ash and smoke and reconstruct the original text. The current thinking is that something similar happens with black holes. The information isn't destroyed. It's just incredibly scrambled and imprinted on the faint glow the black hole emits over billions of years. We don't have the final answer, but we now have a strong theoretical roadmap that suggests the universe's most fundamental laws hold up, even in the face of a black hole. Could black holes be dark energy? The paradoxes inside black holes are mind-bending enough, but what if their dark side reaches out to shape the whole universe? For decades, we've known about another deep mystery: dark energy. Our measurements show the expansion of the universe is speeding up, not slowing down. Something is pushing everything apart, a mysterious force that makes up about 70% of the universe. We call it dark energy, but we have no clue what it is. Now, a fascinating, if speculative, new theory proposes a wild connection. What if black holes are the source of dark energy? This idea, called cosmological coupling, suggests that black holes aren't just sitting in space. They're fundamentally linked to its expansion. As the universe expands, this theory says black holes can gain mass not just from eating stars and gas, but by absorbing the energy of the expansion itself. In this picture, black holes become cosmic recyclers, turning matter into vacuum, energy, dark energy, which then drives the universe to expand even faster. This is a bold claim, but it comes from an intriguing observation. One team of astronomers looked at supermassive black holes in ancient, quiet galaxies over billions of years. These galaxies haven't made new stars in a very long time, so their black holes shouldn't be growing much. Yet the study suggested these black holes are far more massive today than they were in the past. Way more than could be explained by them eating stray gas. While this is far from settled science, and the idea remains highly debated, it perfectly matches the growth predicted by cosmological coupling. If this theory holds up, it would completely change how we see black holes not as passive sinkholes, but as the active engines determining the ultimate fate of our universe. Are black holes dark matter? The universe has another dark secret, dark matter. Some invisible stuff that makes up about 80% of all the matter out there. We know it exists because we see its gravity pulling on stars and galaxies, but it gives off no light, so we can't see it. For years, scientists hunted for new, exotic particles to explain it, but the search has come up empty. This has led some physicists to wonder, what if dark matter isn't a new particle at all? What if it's made of black holes, not the huge ones left over from stars, but primordial black holes? These are hypothetical black holes that might have formed in the chaos of the very first second after the Big Bang. When superdense pockets of matter could have collapsed on their own, these primordial holes could be tiny, some smaller than an atom, but with the mass of a mountain. If enough of them were made back then, they could be scattered all through the cosmos, providing the extra gravity we see. While recent observations have ruled out some sizes of these ancient objects as the main source of dark matter, the search is still on in the ranges we haven't checked. Other ideas trying to link black holes and dark matter get even stranger. Some theories imagine a whole dark sector of the universe with its own particles and forces which could form their own tiny black holes. These ideas are on the very edge of physics, but they show how the mystery of black holes is tangled up with the mystery of dark matter. If we solve one, we might just get the other for free. Echoes from the dawn of time, the deepest connection between black holes and the dark universe might come from the Big Bang itself. One of the big puzzles in astronomy is how supermassive black holes got so huge so fast in the early universe. There just doesn't seem to have been enough time. One radical idea suggests that a strange event in the universe's dark sector could have triggered the creation of massive black holes almost instantly, a birth that violent wouldn't have been silent. The collapse of all that matter would have sent powerful ripples through space-time, gravitational waves. These ancient waves, still traveling across the cosmos after 13 billion years, would carry the unique story of how they were born. We haven't detected them yet. But the next generation of gravitational wave observatories are being designed to listen for exactly this kind of signal. If we can one day hear those faint echoes from the dawn of time, we might find the proof that the biggest objects in our universe were born from its darkest secrets. Our journey into the new dark side of black holes shows that they are so much more than cosmic destroyers. They're where physics breaks down and new ideas are born. They might be the key to the biggest puzzles in science. The exploration is far from over. If you love digging into these great mysteries, make sure you subscribe and hit the notification bell so you don't miss our next trip into the unknown. What started as a journey into darkness has revealed a universe of incredible possibilities. Black holes are no longer just the end of things. They might be the beginning of others. They are the frontier where our best theories fail, and where the path to a new understanding of reality might begin. The information paradox suggests they're the universe's master data scramblers, not its shredders. Emerging theories paint them as possible architects of cosmic destiny, fueling the expansion of space itself. And other ideas propose they might be the very dark matter that holds our galaxies together. The dark side of black holes no longer just means their inescapable gravity. No, represents their potential connection to dark matter and dark energy, the great unknowns. They are the place where the very large meets the very small, where the past meets the future, and where what we know meets what we don't. It forces us to ask a profound question. Are we living in a universe that was not only shaped by these strange objects, but is still being driven by them today? The answers are waiting for us, hidden in the shadows.